Swayam Prabha. Digital India. Educated India.
So, we will continue with our discussion on the thermodynamics of protein unfolding, and as we were talking yesterday, that protein stability is one of the key issues that people who are working with proteins, especially biophysical researchers or researchers in biophysical or the field of biophysical chemistry, they worry about. And what we said was measurement of protein stability gives an idea of the various forces involved, and if you would be doing mutations, then that can bring about changes in protein stabilities, and how would you look at those. How to study stability? We said that we need to measure the free energy of unfolding, right, and the free energy of unfolding is given by this, where D is the denatured, N is the native, right. And we also what we also made note of was that what we are going to talk about are equilibrium measurements. So, that means we have to be at equilibrium, and if it is equilibrium, that means either we go back or forward, we should be able to come back to the same point without losing any information. Essentially, it should be reversible. And why we care about equilibrium, or why are we so much focused on equilibrium? Because you know, we have this relationship between delta G and K equilibrium, right, and delta G is directly related to that, and hence if the system is not in equilibrium, there are many cases where we will discuss later that the system is not reversible, that means the system is not in equilibrium. In that case, you cannot actually do this analysis, right. So, the bottom line is that you have to have the system in equilibrium. Okay. So, what are the possible methods to unfold a protein? This we looked at. One was thermal, one was chemical, one was pH, and the other was pressure, right. And again, the main idea is that you perturb the equilibrium and determine the fraction of protein folded or unfolded. Now, since we are doing what should I say, since we are doing a denaturation, that means we are going to the denatured state, we would rather look at the fraction unfolded or the fraction denatured. Okay. So, this was actually one of the starting points of a discussion on protein denaturation. So, what we are looking at was we are looking at two different proteins, ribonuclease and apomyoglobin. Y is an observable. Now, what do you mean by an observable? Y is a signal, right, a signal which you observe. That means you take a protein in a container, say in your sample cuvette, right, and you do a change in temperature. That means you increase the temperature, and the effect of this temperature increase or temperature change is registered by some observable, by some signal, and that is what Y is. So, what are the few signals that people commonly use? One is ellipticity. I do not know whether you have heard about the technique circular dichroism. So, circular dichroism will give you an observable signal. So, that would be one Y. There is another technique called fluorescence. So, fluorescence will give an intensity change, that will be an observable for us. Now, there is another technique called absorption or UV visible spectroscopy, right. So, there also you can have a change, and that will be a corresponding Y, and many like this, right. So, that is an observable, something we are measuring. Now, between ribonuclease and apomyoglobin, what we said was, though they have different transition profiles, that means different ways of going from. So, if you look at this arrow, so the blue one is ribonuclease here, the red one obviously is apomyoglobin as told out here. And if you go from the low temperature to the high temperature side, what you essentially do is you are spanning across three regions of the transition. And what are the three regions? If you look at the low temperature side, you follow the arrow, if you look at the low temperature side where it is written native, it means that you are at the low temperature, the protein is in a stable form, and hence you are in the native region, right. And then you increase the temperature, and suddenly what happens is, from here, say from you follow this arrow from here to here, you have a huge change within a small range of temperature. That is actually a transition range, right. And then after the change is done, then you go from here to onwards. So that is what? That is your denatured state. That means you have already denatured, you have already gone over to the denatured side. That means your system has mostly is consisting of now denatured molecules, because you have raised the temperature, and hence everything after that is your denatured, corresponding to your denatured state. So one is your pre-transition, which is the native one is the transition where the actual transition occurs, the sharp change, and the other one is your post transition, right. Now the other thing we said was, if you look at these two important parameters, Tm for both the proteins. So what is Tm? If you remember, we had discussed that this T was or Tg, right, what we had discussed before. Tg is the midpoint of some spectroscopic signal, a spectroscopically determined transition signal or transition, right. So this is essentially what midpoint means. That means it is a midpoint of your transition from the folded to the unfolded state, okay. That is what Tg is, and here Tg has been replaced by Tm, the same thing. So that is what it says, Tm is equal to Tg. M either stands for melting or midpoint, it does not matter which you refer to. And what is the characteristic of Tm? The characteristic of Tm is that this is as it says the midpoint. That means here K equilibrium is equal to 1, and if it means K equilibrium is equal to 1, that means it is K equilibrium is equal to concentration of denatured over concentration of native. That means both these have equal populations. Okay, before I move on, there is one more comment I would like to make. The comment is this: see, suppose you are looking at free energy changes, right. Your free energy change is related to equilibrium, delta G is equal to minus RT ln K equilibrium, right, that is what it is. Now if your free energy is related to K equilibrium, now what will happen is, to get a reliable free energy, we should be in which region or which region of this transition you think? Remember, I can only do equilibrium measurements, or those measurements are meaningful if I have measurable concentrations of both the denatured state and the native state. Isn't it true? See, if my K equilibrium is either on this side or on this side, it does not make any sense, because my equilibrium is wholly on either one side or on the other side. But what I am doing now is, I am trying to do equilibrium measurements, and equilibrium measurements are best done if I have measurable proportions of both of these. Where would you have that? Right, or you would be having something in the region which is in the transition close to the Tm. So that is why, remember, if you are doing any equilibrium measurements, you are better off being in the transition region rather than being in the corresponding baselines, which is the pre or the post transition baseline. So always you focus on the transition region, that gives you the best value, right, because here both of those, the natured the denatured and the native states, are populated to a significant extent. Okay. So these are the different regions we talked about yesterday. Now let us look at this. This is also what we refer to. If this is a curve, so what we are doing now is, you look at the black points, you look at the black dots out here in your in this curve, you look at these black dots. So these black dots are your experimental points. That means you have at any given temperature, you have measured the signal y, and this is how the transition moves as you increase the temperature for a particular protein. Okay. Now what is the red line? The red line is a fit. You are trying to fit this curve and extract certain thermodynamic parameters, right. Now look at these blue lines. Let me move further, scroll further. So what are these blue lines referring to? You look at this blue line, which is referred to as Yn. What does it mean? Remember, we talked about pre-transition and post-transition baseline. See, we have to know what is the actual value of Yn. What is Yn? Yn means, I will write it down later, Yn means the observable for the fully native state. What is Yd? Yd means the observable for the fully denatured state. But you see, when I am varying temperature, what is happening? this is these slopes, you can see these lines are not parallel to your temperature axis, that means they have well defined slopes. So, what you do is you define your yn and yd in this form, that your yn is equal to mn times T plus B of n, right. So, again what is yn? Yn is the signal we are getting from the pure native state. This is equal to mn times T plus Bn. What is T? Temperature. Remember, our signal from yn is depending upon temperature, because the slope is not parallel to x axis. So, then I mean the line is not parallel to x axis, it comes with a defined slope. So, that slope is defined by mn, and then you have, obviously if you are having a straight line, you will be having an intercept which is Bn. Okay. Now, the same thing happens with yd, exactly the same way. So, this is yd, this is the blue line corresponding to yd, and then you have md times T plus B of d, the slope for the transition for the baseline of the post transition, and then B of d is the corresponding intercept as it is written out here. Okay, these are two things. So, what you can see is in yn and yd, how many parameters do you have which you need to fit, because this you do not know, you have to fit somehow. How many parameters do you have? See, for yn you have two parameters. What are the parameters? M of n, B of n. For yd, how many parameters do you have? M of d or md, bd. That means you already have 4 parameters which you have to vary when you are going to fit these experimental black circles to this red line. That means this is your fit line, right. Okay. So, before going to the relevant thermodynamic equations, keeping this in mind, let us look at some basic equations. So, what I am going to do is, or what we are doing rather here is this. What we are looking at is, we are looking at the protein going from the native state to the denatured state. Okay, that is what we are looking at. Now, my observed signal y, this is my observed signal at any given temperature, right. See, y is a function of T, right, because you see it changes as a function of T, that is temperature. At any given temperature, it should be having contributions from how many species? You can have contribution from the native state, you can have contribution from the denatured state. So, what I can write is, I can write y is equal to fraction in the native state times the signal given by the native state plus fraction in the denatured state times the signal given by the denatured state. Clear? Okay. So, that is, say this is 1 for us. Now, there is one more thing. Based on the way we have written n going to d, that is the native state of the protein going to the denatured state, what I can also write is f of n plus f of d is equal to what? 1, right, because these are the only 2 species present. Now, when we are saying this, now this is very important. When we are saying this, what do we mean? What we mean is, careful listen to this, what we mean is we have only 2 states available. What are the 2 states? The 2 states are the native state and the denatured state. We are not considering any other state. I will tell you what I mean by any other state. That means, for example, so to diagrammatically represent it, I have a state which is native, okay, it is a compact form, a globular form, and I have a state which is denatured, right. I am just looking at an equilibrium between these 2 at any given temperature. But you can easily raise a point. The point is that what is the surety or what is the guarantee that I would not be having any intermediate states between n and d? I can have, but this is the simplest way I can represent a transition, right. So, this n to d is often referred to as a 2 state model. This n to d is often referred to as a 2 state model. Again, please try to understand the relevance of this. By 2 states, I mean that I have a native state and I have a denatured state, nothing in between. That was number 1. Number 2 is, if you are considering a native state and a denatured state, please do not think that the native state is only one structure or the denatured state is only one structure. What we mean is that in the native state you have an ensemble of structures, that means quite a few structures which belong to the native state, that means which are characterizing the native state. They have very similar properties. In the denatured state we have quite a few structures, quite a few conformations which are very similar to each other and constitute the denatured state. It is not just one structure. It is, remember, if you remember what we discussed for protein folding, you lose a lot of entropy, right, when you come from the unfolded state to the folded state. So the unfolded state is having a lot of entropy, it will always move around, right, it is so flexible, hence it is very hard for you to pin down on one structure. So the denatured state will always be having an ensemble of structures. Now same for the native. Why? Because no protein is rock solid. That means if you look at a protein, it does not mean that the protein has only one structure, it can have only one structure. Every protein is dynamic, it shows movements, and whenever this protein will show movements, there will be certain conformational changes and you will get a host of structures which again corresponds to the native state. So is it clear what I mean by a two state transition? A two state transition is only having two ensembles, a native ensemble and a denatured ensemble. Okay? So that means I can write, so this is my native ensemble and this is my denatured ensemble. Okay. So that is one. Now based on this, based on these two equations, what I can do is I can write y is equal to, now f of n has, there is a relation between f of n and f of d. So f of n would be equal to what? 1 minus f of d, then I can write y of n plus f of d, y of d, right. So let this be equation 3 for me. Okay. So let us simplify now. So then I can go on simplifying, I said, right. So y of n minus f d y of n plus f of d y of d, okay. Or the next line I can write y minus y n is equal to f of d y of d minus y of n, or now see what we have done. We have said that f of d is equal to y minus y n over y d minus y n. This is equation 4. Clear? Now what is the significance of this equation? Can someone tell me? See, initially we started with f of d f of n, right, but see, we are not measuring f of d f of n directly. What are we measuring though? We are measuring the observable y. So what now you have is, you have expressed f of d, which is the fraction of the denatured state, in terms of your observable y. Okay. So if you look at the numerator, what does it give you? The numerator gives you y means y observed, you are doing the measurement, yn is that, remember that baseline thing, yn is equal to mnt plus b of n, and then you have yd minus yn. Now to understand it is very simple. What are you going to do? F of d is a fraction denatured. So what does y minus yn tell you? Y minus yn tell you how much you have moved away from the native state, that means how much you have denatured, right, that is the difference. Now what does yd minus yn tell you? Yd minus yn, remember, if yd is belonging to the pure denatured state and yn to the pure native state, that is the maximum difference you can have between the two observables in terms of y. So hence your f of d is just y minus yn over yd minus yn. Even without actually doing this derivation, you would have been able to write it down. Okay. Now this is equation number 4. There is one more thing we know. We know that we are always maintaining equilibrium condition. So what do we have? So we have k equilibrium is equal to, what should I write? Concentration of d over concentration of n. right. So, this can be written as f of d over f of n, or I can write k which is equilibrium. Now, I am just writing k is equal to f of d by 1 minus f of d. Okay. So, this would be equation number 5 for us. Now, what is the importance of this step now? Remember, again we are doing equilibrium measurements. Equilibrium constant is very important for us, and we have to relate the equilibrium constant to your observable. What you have done is you have equilibrium constant is related to your concentrations or fraction, whatever, that is what you have looked at, but you know there is a relation between what, f d and y in terms of yn and yd. So, you actually have a relation between k equilibrium and the corresponding observables, right. So, then let us write that down. So, what I can write is, using equation 4 in 5, we have k is equal to f of d, which is given by y minus y of n over y d minus y of n full divided by 1 minus y n over y d minus y n. There is another expression for k, and hence, so k would be equal to, what will it be? It would be y minus y of n. Then what do you have in the denominator? Y d minus y, and this would be what, equation number 6 for us, I guess. See, again it makes sense, right. What was your equilibrium constant? Equilibrium constant was essentially f of d by f of n. What is y minus y n? It is the amount by which you have moved out from the native state, right. And what is y d minus y? Y d minus y is the difference between what, the denatured and the y, that means the amount you have moved away from the denatured state. So, which is essentially f d over f of n. Okay, makes sense. Okay. Now, what is the last piece of information I need now? There is still one connecting equation we have to connect. Remember, we are always going for what, delta G, free energy. So, the last information is, or the last equation is, there is the last piece of the puzzle, that delta G is equal to minus R T ln k equilibrium, or minus R T natural log f of d by 1 minus f of d, and there should be 7. See, by doing this, you have actually achieved a huge thing. You have related delta G to what? You know delta G is related to k equilibrium, but not only that, you know k equilibrium is related to f of d is related to what? Y, yn and yd. So, you have related delta G to what? Your change in observable. Having done all these things, see, all these things were pretty easy, right? You know it. The assumption was that it was a two-state assumption, that is what it was. Otherwise, it was just straightforward, and everything fell in place, and we finally managed to connect what? The stability parameter, which is delta G, that is what we always go for, through the observed signal you are getting, right. So, now if you carry on with this, after we have these equations, these set of equations, you know, you also know these relevant thermodynamic equations, right. So, delta H is equal to delta H T m plus delta Cp T minus T m, where your reference temperature is not T g now, it is T m, because I said T m is equal to T g, and you have these host of relations, and finally, you can see this delta G, right. We derived this equation yesterday, is related to delta H m T m delta Cp. You do not have anything else. Okay. So, T m is the reference temperature, and delta Cp is the change in heat capacity upon denaturation. Now, how do you actually fit your curve? Remember that we had these black circles or black dots, and there was a red line passing through the curve. So, that red line was the fit to the curve. It is called a non-linear least squares fitting routine, or that is a fit rather. So, this is what you do. This is an equation describing delta G unfolding, that means you are going from the native to the denatured state as a function of t. Okay. You have k, which is given by this relation. You have fd, which is given by this. I have derived that. Okay. Now, here if you see at the bottom, so these all three equations are referred to as a set of nested equations. You know what happens in nest? Nest means you have everything together, right? You have this mesh. So, these are nested equation, means all these things, all these equations are related to each other in some sense or the other, okay, by through observable parameters. Next, what is k? K is equal to y minus yn by yd minus y, we just derived, and then remember we are doing this as a function of temperature, hence I can express y in terms of this yn, yd and k simply. I am just rearranging this equation to express this like this, no problem, right. And the only thing I have done is I have put in a temperature T. Why? Because I know I am doing a temperature dependent denaturation or unfolding or transition. So, see, you have y of t is equal to y n t plus y d t times k over 1 plus k. You know what the expression for y n of t is, right? What was it? It was m n t plus b n. There are two parameters, right? Now, look at y of d. What do you have? m d t plus b n, again you have two parameters, right? Now, then you have k. What does k depend upon? K depends upon the equivalent the free energy change, right? Now, the free energy change, look at this now, the free energy change is how many parameters now? You have delta H, right? You have delta Cp. So, essentially all these parameters have to be fitted together. That means, when you have that transition curve, that those circles, so if you remember, let us see if I can get there quickly. Yeah. So, if you remember all these experimental points, okay, you are trying to fit these experimental points, which this fit is a red line. So, you need all these equations together to fit your experimentally observed transition. So, the basic equation you are using, let me go through this. The basic equation you are using is this, the last one. The basic equation you are using is the last one. You know what yn is, you know what yd is, you have expressed it, you know what k is, and you fit your observed transition to this equation. This is called a non-linear least squares fitting analysis. Okay? A non-linear least squares fitting analysis, that is what it is called. Okay? And write it down. So, what you are doing is you are doing a non-linear least squares fitting analysis. And hence you will be getting typically all your parameters, Tm, delta G, then you will be getting Mn, Bn. So, essentially what you will get is you will get Yn and Yd, which are the spectroscopic signals of your pure, native and denatured. Now, let me make this point before we move on. See, it is very hard to get this Yn and Yd. What do you mean by that? When you are at the room temperature where the protein is more stable, your K equilibrium is almost towards the native state, but even though it is towards the native state, remember you always have, no matter how much small, a fraction of your denatured molecules out there. So, essentially it is not your pure native state. Similarly, when you go to the other side, you have essentially a denatured state, but you still have it mixed with a little amount of, no matter how small it is, a native state, right, some native conformations. So, essentially what you do is, it is very hard for you to measure the actual yn and yd, and that is why this nonlinear fitting routine gives you the absolute signal of yn and yd. Because why do we need the absolute signal? Because the absolute transition is defined by what? The difference between yd and yn, because those are the maxima. Your final transition, your final observable cannot be more than yd, the other observable yn or whatever you are starting from, it cannot be lower than yn, because you have to start from the pure native and then you go to the pure denatured. That is what you are trying for, that is what you are looking for. Is it clear? Now, this is one way of fitting your thermal transition. So, that is what it says, the observed signal yt can be fit to the above equation to get the corresponding thermodynamic parameters. Okay. All these equations are interrelated. Now, what is an alternate method of analysis? The alternate method of analysis is this. You know the Van 't Hoff's equation you have done in thermodynamics. This is a relation between your equilibrium constant and delta H, right. So, this can also be written as, there is a two different derivative forms, dl and k of d of 1 by t is equal to minus del H by r, okay, where del H is the change in enthalpy obviously and k is the equilibrium constant. So, now what I can do is, remember I had this equation of y in terms of yn, yd and k. So, instead of putting the other equation of k, what I do is I put in this k, and what I know from this equation is k will give me this expression. So, I have just put in there and I do an analysis on that, I do a fitting on that based on y of t. Okay. See what I have here, is I still have yn, I still have yd, I have delta hm, I have tm, but I do not have delta cp here, though I have delta hm. Okay. So, this delta hm with a van on top means, on the superscript means Van 't Hoff's enthalpy change at the midpoint of transition Tm. Now, the question is, how do you estimate delta Cp? If you rigorously, very academically rigorously, if you want to do a delta Cp calculation, this is what you should do. Measure thermal denaturation at a range of pH values. Slope of delta Hm versus Tm will give you delta Cp. Okay. How? So, this is the experiment that was done. What you do is, see what will happen when you change pH, your protein stability is dependent upon pH, right, and Tm is what, the midpoint of your denaturation transition. So, that Tm will also depend upon pH, right, because now you are changing the stability of the protein. So, what you do is you do thermal transitions at different pH values, say one is pH 4, one is pH 6, one is pH 8, one is pH 9, whatever. Now, what will happen is, when you do this thermal denaturation transitions at different pH values, you will be getting for every pH different Tm values, right, because Tm is dependent upon the protein stability. Now, then what you can do is you can plot your delta Hm from your Van 't Hoff's analysis against this. I should have written here, maybe I am see, yeah, you can plot delta H Van 't Hoff versus T of m, and remember this is the slope. So, delta of delta H over delta T gives you what? Delta Cp, isn't it? Because the slope of the change in enthalpy, or rather the derivative of the change in enthalpy with temperature, is your delta Cp. Okay. So, that is what it says. If you look at these three different curves, this is a certain pH. Okay. So, this is another pH, this is another pH, and you can see what are the delta Cp values available. They have even given you, it is 1.51 with this corresponding standard deviation. So, they are very close to each other. This is an experiment which has been very carefully done, and you can see the average values are very close to each other. So, your average Cp is, or delta Cp is 1.52. Okay. So, this is one of the best ways, if you really want to be thorough with your research, this is one of the best ways of getting your delta Cp. And remember, delta Cp is the one which defines the change in delta H, which defines the change in delta S, and it also defines what? One more thing. What was the relation of delta Cp with delta G? Remember the stability curve? What was delta Cp related to? The curvature. Delta C is related to the curvature of your stability curve, isn't it? It also gives you that relation or that information. That is why delta Cp is so important. So, anyway, so if you really want to do an analysis, a thermal transition analysis, you want to get the corresponding parameters, and these are different ways you can do it. Is it clear? Okay. Now, this is where we considered only two states N and D. What happens if we have more than two states? So, what I am talking about now is, okay, we have looked at a two state scenario. Now, suppose I have a scenario where I can have say N in equilibrium, say an intermediate I 1, in equilibrium with an intermediate I 2, and so on, and finally I have say I n in equilibrium with D. So, all these i's are referred to as my intermediates. Then this is no longer a two state transition. This is no longer a two state transition. Okay. But I can take care of it, at least I can try to take care of it like this. What I say is, initially y was equal to, when it was two state, if you look at this equation which is on the slide, y was equal to f n y of n plus f d y of d, right. That was, so up till this arrow, where the arrow is, it was a two state, but now you are saying you have intermediates. So, what do? You take a summation of all the intermediates that can be present, okay, and with the corresponding fractions. So, that is the small change you bring in your basic equation. Then everything follows the same way. I is the ith intermediate, and then you know that f n, so the summation of all the fractions should be equal to 1, right, and f n is given by this, the fraction of the native state is given by this. Okay. So, then what follows is, I will go through the same drill. That means, again I will try to relate f of d or f of n, I will try to get k, and I will try to get delta g and go through that fitting routine possibly. Okay. So, what are the next set of equations? Here what I do is, instead of writing f n or f of d, what I say, I write f apparent. Why do I write f apparent? Because I know that this is not only one denatured state, I can have many intermediates now. So, then what I say is f apparent, the expression still remains the same, but what has changed is, you can see it is f d plus sigma f I d I, okay, where d I is given by this y I minus y n over y d minus y n. Now, the significance of y I is the corresponding signal of the ith intermediate, and y I minus y n signifies what? How much you have moved out from the native state, right, and y d minus y n is, you know, always the absolute value. The constraint is that d I is between 0 and 1. What do I mean between 0 and 1? That means, if d I is close to 0, where am I? If d I is very close to 0, or if d I is very close to 1, if d I is very close to 0, I am say very close to the native state. If d I is very close to 1, I am very close to the denatured state. So, my assumption is that whatever intermediates I have, they have to be between the native state and the denatured state, hence 0 and 1, right. Okay. So, as it says, range of d I signifies that physical property of the ith intermediate that lies between that of denatured and native states, essentially that physical property. Okay. Now, I go for k apparent, again the equilibrium constant. So, this is given by the same relation. We already know what k apparent is, it is the apparent equilibrium constant, and 1 minus f apparent is the apparent fraction of native species, right, because f apparent constitutes of everything starting from your denatured state to all the intermediates. So, 1 minus that would essentially give you what? Your fraction of the native state. Now, what you do is, you introduce true equilibrium constants. What do you mean by true equilibrium constants? If you have an equilibrium between the native state and intermediate I 1, say, then equilibrium constant between this k is equal to concentration of I 1 divided by concentration of n, right. So, that is why you see what is k I for me? K I is fraction of the ith species which is the intermediate over f of n, and Kd is definitely what it is defined by. Okay. So, now you can go through this, you will get a host of relations like this, right. So, that is another point. Let me try to make the last point. So, look at what your K apparent is now. Your K apparent, okay, you can do these derivations. Your K apparent is given by this relation. What does it have? Your K apparent has Kd, right. It also has Ki, and it has the Di, the one corresponding to that ith intermediate, the physical observable. Okay. You do not need to write down so quick, it will be on the slides. Maybe you want to derive it, but I am not so keen on that now anyway. So, the point is only the apparent equilibrium constant K app is measured and not Kd, because as we just saw, K app not only has Kd, but it also has information on Ki, right. So, this is why it is called K app, because your apparent, because your equilibrium constant is not only Kd, it also has contributions from your respective Ki's. Okay. So, you just cannot do it like that. That is why it is called the apparent equilibrium constant. See how much it has become more complicated when you just shifted from a 2-state to a multi-state model. Okay. Now, what you can do is, if Ki is equal to 0, what will happen? If Ki is equal to 0, what will happen? Then your K apparent is equal to Kd. You fall down to what you have just derived. So, this is your most general equation. From this you can go anywhere. Okay. That is the idea. Now, if Ki is not equal to 0, okay, and K apparent, then obviously is not equal to Kd, even if Di is equal to 0. Now, this you have to understand. If you look at it, see, Ki is not equal to 0, right. Okay. Even if Di is equal to 0, what do you have? You still have Ki remaining. That means even if Di is equal to 0, your K apparent is still K apparent, it still depends upon Ki. Okay. So, that means even if Di is equal to 1, which is native like intermediate, that means very close to the native state, or Di is equal to, Di is equal to 0 or Di is equal to 1, where intermediates behave like a denatured species, still your K is K apparent, okay, because your Ki is not equal to 0. So, that is another way of looking at it, especially when your transition is not a 2-state, but involves many intermediates. You can try to derive this by yourself. It is very easy. It is just a lot of algebra you have to go through, but it is the same thing. But now the question is, we have talked about a 2-state model and we have talked about a multi-state model. How would you differentiate between these? That is the obvious question, right? How would I know, looking at a transition, how would I know whether this one is essentially a 2-state model or this one is not consistent with a 2-state model? That is an obvious question, right? There should be a reason why you are going to this, because we have to try to answer that. So, this is what brings us to the next topic, which is called investigating the unfolding mechanism. How do we investigate that? Is it a 2-state? Is it a multi-state? If the unfolding curve shows multiple steps, then the process is not 2-state. Now, what do I mean by multiple steps? Multiple steps, what I mean by multiple steps is this. That means, remember, for a 2-state, say if something is strictly 2-state, you see a transition which goes like this, say, right. This is a 2-state transition, this is y and this is t. Okay. Now, if you have more states, if it is a multi-state transition, then it might happen that you have transitions which look like this and so on. Then if you have transitions like this, you can always see what happens. From here to here is one state, from here to here is another state, from here to here is another state. That means you are all looking at different intermediates and finally you go to your denatured state. So, if you have, so suppose you are doing this measurement where you are measuring y, and if your y is behaving like the one you have for the multi-state, then it is a multi-state model, it is not a two-state model. However, if it is behaving as y as the two-state model, that means you do not have any other transitions, you can say okay, there is a possibility of this being a two-state model, but you cannot say that it will be a two-state model. Why? Why? Because in a two-state model, look at this, in a two-state model what will happen is, or look at the multi-state, in a multi-state if the corresponding equilibrium intermediates, the concentrations are really low, then you would never be able to figure out these transitions, because the presence of those species are really low. What essentially we will look at is either this one and the last one. So, then apparently it will look like a two-state model, but it is actually not a two-state model. That is why when we see a transition like this, we do not say that it is definitely a two-state model. What we rather would prefer saying is it is consistent with a two-state transition, but we do not know for sure. Okay? We do not know for sure because of the complexity of the process, right. So, that was one. Is this clear? What do you mean by a two-state and multi-state if you have transitions like this? Okay. Let us go back to the slides and let us look at the next slide. Now, even if a single step unfolding is seen, it does not guarantee that the transition is two-state. Even if a single step unfolding is seen, it does not guarantee that the transition is two-state. That is what we just discussed. You might be having these intermediates which have very low concentrations or very transient existences, they do not contribute that much to your folded that much to your signal, you will not be able to detect, but that does not mean that they are not there, they are there, hence it is not strictly a two-state. Okay. What is the test for the intermediates? A test for the intermediates is to plot F apparent against temperature T using several different physical properties, that means using different techniques. What does it mean? Remember the di was the physical property of every intermediate. So, think about this. Suppose you are doing a CD, suppose you are doing a fluorescence, and suppose you are doing some other technique. That physical property di would under all circumstances not be the same for these different techniques. Why? Because these techniques are looking at different things, they are probing different things. In fluorescence, you are probing the fluorescence of a fluorophore. Now, we will talk about this later in details much more. You are looking at a fluorophore which is actually very local, that means it is situated somewhere in the protein, that is a one point say. When you are talking about CD, I mean just take my word of mouth right now, I will explain this to you later. When you are talking about a CD, suppose you are doing a secondary structure analysis, then you are looking at the whole protein unfolding, that means you are looking at the whole protein. In fluorescence, you are not looking at the whole protein, you are looking at a specific portion of the protein. So, immediately then you have a difference in di, okay, and then if you take another technique, you will be having something else coming out, right. So, that is why di's are definitely different in different techniques. So, what it says is, if the plots are coincident, then a two-state analysis can be used, or it is consistent with the two-state analysis. Now, do you understand this? See, we just discussed that if you are going to use different techniques, then your di is not necessarily the same. If your di is not necessarily the same, remember your k equilibrium or k apparent was dependent upon di, ki and kd. So, F apparent was also dependent upon that. So, if your di is not the same and if you will be using these different techniques, when you would plot F apparent versus temperature for the different di's, your plots would be different because the di's are not the same, right. If the plots are different, then you immediately know that you have not a two-state, you have a multi-state transition. However, if plots are almost superimposable with each other or almost identical with each other or very similar to each other, then what you can say safely is that whatever di I am looking at the same thing, and essentially I have only two states, the native state and the denatured state, okay, consistent with. See, I am not saying it is a two-state, I am just saying it is consistent with the two-state model, right. So, as it is written out here, when F apparent versus temperature is measured for several different physical properties, the values of F app should vary if intermediates exist, that is what we just discussed, because DIs are different for the different techniques. Now, a given DI is not expected to be the same for each distinct physical property, that is what we said. In one case you are doing CD, in one case you are doing fluorescence, different properties, not necessarily the same. So, example is, look at this unfolding of protein ribonuclease A. What did they do? They looked at the unfolding of protein ribonuclease A using 3 different techniques. What are the techniques? One is optical density, which is UV visible spectroscopy, absorbance. The other one is optical rotation, I have heard about this. The other one is intrinsic viscosity. Okay. So, they looked at viscosity which is intrinsic to the protein, and I do not have the plot, but what they saw was all of the above showed the same profile for F app, that means F apparent. What does that signify? That the unfolding of the protein, remember again I am specifying this word, consistent with the 2-state model, consistent with the 2-state model. I am not saying it is a 2-state model, it is very hard for me to say that, okay, but it is definitely consistent with the 2-state model, right. So, this is how, given a thermal transition or given any transition per se, you would possibly try to analyze it, keeping all these different things in mind. Is it clear? So, we started from this nonlinear fitting routine based on a 2-state model, then we moved on, invoked intermediates, put in intermediates, and saw how the K apparent and F apparent would change, and then what is the significance of this DI, how does it differentiate between a 2-state and a multi-state, and this is how it does it for us. So, in other words, the bottom line again is this, I am using too many bottom lines, but really this is the bottom line, that if you would try to figure out whether a transition is 2-state or not, what would you do? You would actually use different measurements, that is it. You would use different probes and see whether the unfolding transition you get are very similar to each other or not, and that would be consistent with the 2-state model if they are similar. That is what the take home message is. Okay. So, that was about thermal denaturation. What I will do tomorrow is we will do chemical denaturation, we will look at chemical denaturation, what it is all about, and I will see whether I can finish off with chemical denaturation. If I can, then I will move on to pressure or pH. If not, because chemical denaturation is also very kind of interesting. It is based on the same principle, all the basic equations remain the same, but remember, in case of temperature you vary what? Temperature, right. So, delta G varies with T, but in this case you are doing it at the same temperature and you are varying what? Concentration of denaturation, see urea or this guanidine hydrochloride. That means it is essentially an isothermal experiment, is not it? That means your temperature is the same. So, it is no longer delta G of T, it is delta G as a function of something which is known as urea concentration. That is what we are going to try to find. Okay.